Okay, we're going to go ahead and get started. My name is David Freyer. I'll give you a quick observatory report and then hand it over to our speaker, who's Anish Roshi. So what's going on at the observatory? We finished the painting, and it was successful. And we're now reinstalling receivers and reconfiguring the LOs and IF systems. So we're getting the system's up and running basically in preparation for the startup, which will start towards the end of September. We still need to replace 5 wheels, and that will happen in September. And then we'll have a track week as well where we replace the wear plate. So everything's on schedule for startup at the end of September. So that's what's going on at the observatory. And I will introduce Anish. Anish used to be here at Green Bank. He was a scientist here that helped build Vegas, our current spectrometer. But today he's going to be talking about science. He's now at the University of Central Florida, and he's going to talk about the detection of helium recombination lines in Cygnus X diffuse ionized gas. And I just remind the participants, you can ask questions in the Q&A at the end of his presentation. So go ahead and take it away, Anish. We can see your slide.
Okay, thank you, David, and thank you for inviting me for giving this talk. So as David said, I will be talking about the detection of helium towards Cygnus X DIG, the diffuse ionized gas. My collaborators are listed here. Pooja is a PhD student who is working on this project, and this paper is now accepted for publication in Astronomical Journal. So I'll first talk about the helium ionization problem in the diffuse ionized gas. Then I'll talk about Green Bank Telescope recombination line observations we made towards Cygnus X region. So we are considering Cygnus X region as a test case to see whether we can detect helium from the diffuse gas associated with the Cygnus X region. And in fact, we detected helium at 800 megahertz. And this is the first detection of helium from the diffuse ionized gas in Cygnus X region. Then I will talk about the properties of this ionized gas, how we derive the properties of this ionized gas. And what we found is that the helium that we detected towards the Cygnus X region is originating from a low-density ionized component or low-density ionized gas, which has physical properties similar to the DIG in the inner regions of the galaxy. But the previous observations of helium in the inner regions of the galaxy towards the DIG, that's the diffuse ionized gas, has not detected helium. And that's where the importance of this, in my opinion, the importance of this result is. It's not the first detection, but it's the detection of helium from DIG in Cygnus X and the non-detection of helium in DIG in the inner galaxy. And that's what's the interesting part of this project. And I will then talk about the implication of our detection for helium ionization in the inner galaxy and talk about some future plans. Most of you know about the warm ionized medium in our galaxy. It is a thin, tenuous, diffuse ionized gas which is present in the interstellar medium. This has been the presence of this ionized gas was first inferred from radio continuum absorption at very low frequency, about 5 megahertz or so. And a lot of information were derived from pulsar DM observations. And the most of the information later came from the H alpha observations. These are optical recombination lines. And a survey of these optical recombination lines has been done by the Wisconsin University group. And what the H alpha survey showed is that the emission measure of this gas is less than about 1 parsec centimeter raised to -6. These are each of these cloudlets, which is you can think in terms of a cloudlets which is present in the interstellar medium that is part of this warm ionized medium has an emission measure which is less than about 1 parsec centimeter raised to -6. The local density is about 0.05 per cc. The electron temperature can be somewhere between 6,000 and 10,000 Kelvin. As you can see in this image, the H alpha has been detected way above the galactic plane. So the scale height that has been derived for this emission is about 1.5 kiloparsec. And the volume filling factor that has been derived is about 20 to 40%. So it's a large volume filling. This ionized gas fills a large volume of the interstellar medium, and therefore this is considered as a major component of the interstellar medium, and it's called the warm ionized medium now. Now, when you come closer to the galactic plane, you can see there is brightening in the H alpha emission, and most of this brightening is because of the ionized gas in the local interstellar medium. We cannot probe the galactic plane using H alpha because of the interstellar extinction. H alpha is in optical, and therefore people have tried to probe the ionized gas in the diffuse ionized gas in the inner region of the galaxy by doing low frequency recombination line observations. The radio recombination lines won't suffer interstellar extinction, and people have therefore tried to use the low frequency radio recombination lines to see the diffuse ionized gas. And the surveys have detected the extended presence of this extended presence of this radio recombination line emission in the galactic plane. This is a LV diagram, longitude velocity diagram, that was made from the 327 megahertz recombination line survey as well as 1.4 gigahertz survey. The 1.4 is the count-out, and you can see the line has been more or less detected everywhere in the inner region of the galaxy. People have also tried modeling this line emission, and the emission measures they got is about a few times 100 to few times 1000 parsec centimeter raised to -6. The densities were in the range of 1 to 10 per cc. The electron temperature is not well constrained, but it's roughly taken as 8000 Kelvin or so. Observation, it has been found that the ionized gas in the inner region of the galaxy, which was probed by the recombination lines, has only a scale height of about 150 parsec, and it has a very small filling factor. So these are very different from the emission measures, for example, are orders of magnitude larger than what has been observed in the warm ionized medium. And similarly, the densities are also orders of magnitude larger than the WIM density. And therefore, in this talk, I will call the diffuse ionized gas that has been observed in the low frequency recombination lines as DIG, or diffuse ionized gas, to distinguish it from the warm ionized medium. Okay. And the relationship of this diffuse ionized gas with the warm ionized medium is not well established. One of the proposals is that the DIG which you see in the inner galaxy is essentially outer envelope of conventional H2 regions that has been that are present in the galactic plane. So in this LV diagram, the dots are essentially the high frequency, the 5 gigahertz radio recombination lines observed towards H2 regions. And you can see they generally lie in the same velocity range where the low frequency lines has been detected. And based on that, it has been proposed that these H2 region, these diffuse ionized gas could be the low density envelopes of the conventional H2 regions. There is also alternate proposals which tell that which suggests that this could be a denser version of the warm ionized medium in the inner region of the galaxy. Yeah. Now I should mention there was a survey that has been made, a recombination line survey that was made with the GBT at 5.8 gigahertz. The PI of that survey is Lauren Anderson. This survey is called GDIX, GBT Diffuse Ionized Gas Survey, and that has detected lines diffuse emission in the galactic plane. the recombination line emission in the galactic plane, and the angular resolution of this survey is 2 degrees, which is incredible. And there's no way you could get low frequency observations for diffuse gas with 2 arc-minute resolution. It's so this survey is great for its angular resolution. However, I should caution that this 5.8 gigahertz recombination lines, as you will hear later in the talk, can originate from not only from the low density component, but it also can be originating at the higher density components. And therefore, there should be there need to be a GBT low frequency survey, which could be combined with this 5.8 gigahertz survey for understanding the characteristic of the ionized gas that is producing the line emission in the galactic plane. Okay. So now, what ionizes the DIG and the WIM? And it is generally believed that OB stars in the galaxy are the primary source of ionization for DIG. It has been estimated that the total ionizing luminosity from all OB stars is about 3 times 10 to the power of 53 Lyman continuum photons per second. And this has been estimated from one of the ways it has been estimated is by studying the thermal continuum from the H2 regions as well as the diffuse H2 region, which has been derived from the WMAP thermal decomposition of the continuum. And the same study has shown that about 60 to 80% of the photons generated by these OB stars has to be absorbed by the DIG to maintain its ionization, DIG as well as the WIM to maintain its ionization. So if OB stars are indeed responsible for ionizing these extended components, then there are several interesting questions that arise. One is how the photons from these OB stars travel long distances, particularly for the warm ionized medium where it has to travel kiloparsec of distance to ionize this, because any presence of neutral medium, neutral hydrogen will immediately absorb that ionizing radiation. So that is one question. The second is to what extent is helium in this diffuse in the DIG as well as WIM is ionized? And my main focus will be on the second question. How much helium is ionized in the DIG and WIM? So as I mentioned earlier, people have looked for helium recombination lines from the diffuse ionized gas as well as the WIM, and no recombination line has been detected yet, and that is what is called the helium ionization problem. And I will try to explain that. For that, will first consider the ionization structure of helium in a conventional H2 region. So if you have a star that is ionizing the H2 region, what determines the amount of helium that is ionized is the hardness of the radiation from these stars, and which can be characterized by a parameter called gamma, which is essentially the ratio of the Lyman continuum photons with energies above 24.6 EV to those above 13.6 EV. That is the ratio of photons that can ionize helium to the ratio to the photons that can ionize hydrogen. Okay. And this diagram essentially summarizes the structure of this H2 region in terms of the single parameter gamma. The y-axis here is the ratio of the ionized helium to hydrogen volume, and the axis here is a gamma, essentially normalized with the abundance of helium. Okay. So even the gamma is very small, then the volume of helium, ionized helium, increases linearly. But as gamma becomes larger, there will be more photons available for helium to be ionized, and the process essentially asymptotically converges to unity. The volume of the ionized helium to ionized hydrogen converges to unity for very large gamma. So for gamma above about 0.16, the helium-Strontium sphere overlaps with the hydrogen-Strontium sphere. And if that is the case, when you observe recombination lines of helium and hydrogen, their ratio should essentially be the abundance ratio of the helium, which is roughly about 0.1. So the same model you can apply for the interstellar medium. In the case of interstellar medium, the ionization is done. The ionization is not from one star. It will be a cluster of. OB stars are formed in clusters, so you have to consider an effective gamma for the radiation from that cluster, which you can compute if you know what is the initial mass function of these clusters. And this computation has been done, and it has been shown that the gamma of these clusters should be about 0.16, which means the helium and hydrogen Strontium spheres of produced by these clusters should be overlapping, or in other words, the helium in the interstellar medium should be fully ionized. And as I said, we don't see helium observationally, at least in the inner region of the galaxy. The upper limit, which we got, is 0.013 from recombination line observations, while we expect 0.1 if it is fully ionized. And from the optical observations in the WIM, the ratio is found to be about 0.26. The upper limit is about 0.27. So this is basically the helium ionization problem. We expect from, if massive stars are ionizing the interstellar medium, ionizing the warm ionized medium as well as the DIG, then we expect helium to be ionized. But observationally, we don't see helium fully ionized in these regions. So there are a few explanations, few models how we can ionize interstellar medium without ionizing helium. And one of the suggestion is that most of the O6 star, which are the hotter star, which will have high gamma, those stars could be embedded in ionization bound H2 regions. So you will not have much radiation coming out of those H2 regions. So the ionization of the WIM is mostly done by the lower mass stars, which has surface temperature less than 37,000 Kelvin, or their gamma is less than 0.16. So this is one possibility that has been discussed. The other possibility is leaky H2 regions, where when the radiation leaks out of the H2 regions, the gamma changes, and therefore it changes in such a way that the helium in the diffuse regions will not be ionized. Okay, and both these needs to be tested observationally. And I should also mention that in the case of the galactic H2 regions, which are ionized by O6 stars or earlier, you see the line ratio close to about 0.07. Okay, so now I'll come to the Cygnus X observations. So there was 2 surveys that has been done towards the Cygnus X region with the Green Bank Telescope. One is at 340 and 800 megahertz. The PI of that survey was Kim. And there's a second survey which was done at 5.8 gigahertz, and PI is Lauren. And this is the region shown here on the left is the region that has been observed in the survey. It's centered at L is equals to 80 degrees, B is equals to roughly 1 degree or so. And the total area that is covered is about 5.7 degree by 5.7 degrees. The angular resolution at 340 megahertz is about 45 arc minute. 800 megahertz is about 21 arc minute. And at 5.8 gigahertz, the angular resolution is about 2.9 arc minute. And the total telescope time used for this survey is about 48, 60, and 70 at these 3 frequencies, 70 hours at these frequencies. And we have observed multiple transitions within this, within the observing band. And all the recombination lines of hydrogen, helium, and carbon has been simultaneously observed in this survey. the image in the middle shows the integrated intensity of hydrogen recombination lines that has been observed in the survey with the full resolution at the 3 frequencies. And this is a typical spectrum away from all these H2 regions. So you can see the brightest feature here is the hydrogen line, but you can immediately say that helium cannot be detected with this sensitivity because helium is 1/10 of the hydrogen intensity. So what we did is we took these surveys, smoothed it to the same resolution, took all the 3 frequency observations and smoothed the data cubes into the same resolution of 45 arc-minute, which is the resolution of 342 megahertz. And to look for recombination lines from the diffuse regions, we masked out the H2 regions, known H2 regions that has been cataloged in the WISE catalog. So this the image on the right shows essentially the masked image. So the diffuse emission is seen away from the mask, and you can see the scale has changed here. And one thing you can notice is that the brightness of the emission is higher close to the mask, which may suggest that the diffuse gas is essentially the outer envelope of the H2 regions. I mean, that's one of the possibilities. Even after masking, if you, I mean, that will not anyway certainly increase the signal to noise ratio. So we have to, what we did is we averaged all the data in the unmasked region, and the spectra shown here are the average spectra from the unmasked region. In this average spectrum, certainly we have detected the hydrogen line in all the 3 frequencies. We have a helium line detected at 800 megahertz. And there's carbon line detected at 800 and 340 megahertz. Of course, the carbon line comes from not from the DIG, it comes from the photo dissociation region present in the Cygnus X region. And the lines which are associated with the fully ionized gas are the hydrogen and the helium in this spectrum. So then we estimated the line ratios, which is the integral of the line and line brightness temperature to the integral of the line brightness temperature of hydrogen, essentially hydrogen to helium line ratio, which is proportional to the ratio of the number density of ionized helium to the ionized hydrogen, which is what is plotted here in the y-axis. And for various different type of masking which we have used for estimating that. I mean, I have showed one of the masking which we call as the H2 region masking, where we have masked out all the H2 regions. We also tried out other masking schemes, which is the results of that is also included in this plot. At 800 megahertz, the estimated ratio is about 0.06 plus or minus 0.2, which is this point here. At 340 megahertz, we haven't detected the line, but our sensitivity is insufficient to detect helium line at the expected ratio of 0.06. The point is right here. And at 5.8 gigahertz, we detected an upper limit, which is about 0.05. Then we also, in the same plot, I have included what is the line ratio in the masked region. That is essentially what is the average line ratio in the H2 regions within the Cygnus X region. And that turns out to be about 0.05 plus or minus 0.1. That's this point. And as I mentioned earlier, for the Galactic H2 regions, we measured about 0.07, the line ratios, if the ionizing star is 06 or earlier. Okay, so the conclusion from what we draw from this is that helium in the Cygnus X DIG is ionized similar to H2 regions with that has been that would have been ionized by O6 stars or later. It is not like the DIG which we see in the inner galaxy where helium is not detected, but in the case of Cygnus X DIG, we see ionized helium. And the ratios are very similar to the ratios measured towards the H II regions. I forgot to mention in this plot, I have also shown the upper limits derived for the helium lines towards the WIM and as well as towards the inner galaxy from radio lines. And these are the upper limits that has been reported earlier, and we detect it much above that upper limits. So now we'll try to characterize or try to understand what is the physical properties of this ionized gas that is producing this hydrogen and helium line in the Cygnus X region. So first we examine the LSR velocities. This plot here shows the histogram of the difference in the LSR velocity. It's not the LSR velocity alone. It's the difference between the LSR velocity of pairs of frequency. The green here shows the velocity difference between 340 and 800 megahertz, and it nicely speaks at 0, which essentially tells that 340 and 800 is sort of associated. And the 5.8 gigahertz has a velocity which is very different from 340 as well as 800 megahertz, as seen in the blue and the red and the rose histograms. So this essentially suggests that there should be two different ionized components that is producing the lines at these frequencies. One of the component is producing lines, or one of the component emission from one of the component is dominating the 340 and 800 megahertz line, and a second component produce most of the line at 5.8 gigahertz. So then we went ahead and applied non-LTE modeling to get the physical properties of this ionized gas. The details of this modeling you will find in an upcoming paper led by Pedro. Basically, we had recombination line detection, and we also combined it with radio continuum of continuum constraints towards these diffuse regions from 408 and 1.4 gigahertz. So we kept two electron densities for the two ionized gas and the two emission measures of the two ionized gas as free parameters. We had to make one assumption, so we assumed that the temperature of these gases are safe. And what we derived is that one of the gas should have an electron density about 150 to 1,500 per cc. 1,500 is not strictly constrained, it can be even higher. And the emission measure of that component should be between 300 and 1,200 parsec centimeter raised to -6. So we call this the high density component. And the second ionized component has an electron density between 2 and 15 per cc, and it has an emission measure between 750 to 1,600 parsec centimeter raised to -6. So, the low density component here has physical properties which is similar to the DIG that has been observed in the inner galaxy. So there also the densities and emission measures are in this range, which we have derived from the low density component in the Cygnus X region. Now, if you look at the line emission from these two components at the three frequencies, at 340 and 800 megahertz, the line emission is dominated by the low density component, which is shown by the sky blue Gaussian. That is the model prediction that is the prediction from the model. And at 5.8 gigahertz, both components sort of equally contribute emission at the 5.8 gigahertz. Okay, and as you come to the lower frequencies, the emission from the higher density components get pressure broadened, and therefore the peak line emission line emission decreases, and that's the reason we are not detecting much contribution from the high density component at 800 and 340 megahertz. So so the basic conclusion from the modeling is that the 800 and 340 megahertz emission is dominated by the low density component. And because the helium recombination line emission is hydrogenic, it should have the same frequency dependence as that of hydrogen. And since we have detected helium at 800 megahertz, we conclude that that line should be associated with the low density component. So our basic conclusions are that we have detected helium recombination lines towards the DIG in the in the Cygnus X region, and the properties of this DIG is the physical properties is very similar to those that has been observed in the inner galaxy. The line ratio measured is about 0.06 for this low density component, and it is consistent with values that has been seen towards H2 regions that were ionized by O6 stars or earlier. Importantly, our observation is inconsistent with scenario where hot stars are buried inside ionization bound H2 regions, or with the predictions of the leaky H2 regions. So both these models don't apply for, at least for the Cygnus X region. And as I mentioned earlier, the line ratios are significantly higher than the upper limits that has been reported towards the DIG and the WIA. So we looked for some possible explanations of why helium is not detected in the inner galaxy. And the possibilities are same as what has been discussed in the literature. We don't have anything new to add. One of the possibilities that has been detected, that has been discussed, is the presence of some additional source that could produce only hydrogen ionizing photons, but no helium ionizing photons. And one of the possibilities that has been discussed is there are certain B stars which produce more hydrogen ionizing photons than what the conventional models for the B star emission predicts. The other possibility, which is slightly exotic, is that it's possible to have a resonant dark matter decay, which will produce Lyman continuum photons about 13.6 eV, but not at 24.6 eV. The other possibility that has been discussed is the dust properties in the inner galaxy can be different. The metallicity in the inner galaxy is higher compared to the outer galaxy. So the dust property is such that it preferentially absorbs more helium ionizing photons compared to the hydrogen ionizing photons. And that will reduce the number of helium ionizing photons available for ionizing the diffuse regions. So we would like to test these hypotheses, and that's where our new set of data will be extremely valuable. There are two surveys that has been going on as part of the GDIG's LOW program. This is the GBT DIG survey LOW, and we are using two frequencies to do the survey. One is at 340 megahertz and another is at 800 megahertz. And this survey is done in the inner region of the galaxy. The PI of the survey is Pedro Salas from GBO. And this survey is essential for us to understand the helium ionization issue in the DIG in the inner region of the galaxy. And we need 800 megahertz because that appears to give the sensitivity to detect helium. And we need the 340 as well as the existing GDIG's 5.8 gigahertz for model the line emission to understand what are the physical properties of the gas that is producing this helium line emission. So that's all I have to say. Thank you.
Thank you, Anish. for a great presentation. We'll open it up for questions. For those having questions, go ahead and put it in the Q&A window.
Where is that?
Okay. Okay. I have a side question. I don't have a question yet on the talk. Let's see here. There has to be a few questions. I could ask some questions, but so the goal was to cover all the area you're going to complete the 340 at the area that's been covered with 800. And
Yes.
Okay.
So that's where we have some trouble in getting the telescope time because the 340 receiver is not going up as frequent as we want.
Yeah.
So that
we have some the real estate up there at Prime Focus is quite high with the other instrument and such. Okay. Are you going deeper at the 800? Is the 800 complete because it looked like it covered, or is there still more 800 data that you guys would like to get to go deeper?
Yeah, we have more observing time. This is the preliminary data that has been made, but if we can go deeper, that will be great. But we have some more time to complete to do more observations, the 800 megahertz.
Okay. I have a question here. McCallum et al. Has found that the hydrogen recombination times are important in how far the hydrogen ionization occurs. Was this taken into account in your analysis?
Not really. I have to look into the details of that. I'm not aware of that paper.
Okay.
Thanks, Tony.
Okay, you can see them too coming in.
Yeah.
Okay. Next question. More a general question. Do you find that radio recombination lines are brighter at low frequencies or at high frequencies in your sample, or are they fairly consistent regardless of the transition number?
The brightness of the recombination lines, depends on the physical properties of the gas. So, for example, this diagram shows the integrated recombination line emission as a function of frequency. And we had the red line shows the net emission from the two ionized components. The other two lines are the individual contribution from the two components. And as you can see, the low density component, the line intensity keeps increasing as you go to lower frequencies. That's basically because at lower frequencies, the level population gets inverted, and therefore there can be stimulated emission. It's not a true measure; it's a partial mesing effect, which will be more effective for low density gas compared to high density gas. So the intensity of the recombination line at various frequencies depends on the physical properties of the gas, and measuring that intensity will essentially allow us to derive those physical properties.
Okay, thank you. Are there any additional questions? We've run a little bit longer today, but that's okay. We can take a couple more questions if people would like to ask. If not, I'd like to thank Anish again for presenting these results. And I'd like to remind everybody that the next community Zoom will be in 2 weeks, and it's being given by John Cannon. He will be talking about, well, the title is 100 Proof, H1 Observations of 100 Nearby Dwarf Galaxies with the 100-meter Green Bank Telescope. Telescope that we love, and we'll be observing again science in about a month. So we'll see everybody until next time. Goodbye.
Thank you, Dave.
Thanks, Anish.